Hello dear children, hope you all are safe and fine and very eager to study today's lesson. Today we shall study lesson 12 of science, that is electricity, for class 10th. But before we begin with our lesson, I would like to ask a few simple questions from you, and perhaps you have already studied about them in your previous classes, and answering these questions will help to refresh your minds. So children, are you ready to answer these questions? Your first question: what are the two different types of charges? And children, you are absolutely correct. They are a positive charge and a negative charge. My next question: name the different types of subatomic particles present in an atom. And the correct answer is electrons, protons and neutrons. The next question: what is required to light the bulbs, fans, coolers, etc. of your house? And the answer is electricity. Now, my last question for you children is that what is an electric current? Yes, the flow of charge is electric current. Dear children, let us now see that what new we are going to learn today in this chapter. Today we will learn about electric current and circuit, electric potential and potential difference, circuit diagram, Ohm's law, factors on which the resistance of a conductor depends, resistance of a system of resistors, heating effect of electric current and its practical applications. And towards the end, we will discuss about electric power. First of all, let us discuss about electric current and circuit. Children, can you recognize the famous personality shown to you in this picture on the screen? Yes, he is the great scientist Thomas Edison. Do you know this great scientist is famous for what? Yes children, in the year 1869 he discovered electric bulbs, and thanks to him for lighting our homes even after the sun sets. In addition to bulbs, all gadgets like ACs, LEDs, geysers, fan, etc. also run by electricity. Not only this, laser lights and flashlights also work on electricity. Children, does this not compels you to think that what is this miraculous thing called electricity? We are familiar with two forms of electricity. They are static electricity and dynamic electricity. Today in our lesson, we will discuss about dynamic electricity. We already know that charges are of two types, the positive charge and the negative charge. Here, if we try to recollect about the magnets, then we also know that every magnet has two poles, a north pole and a south pole. Like poles, that is north pole and north pole, or south pole and south pole, repel each other, while unlike poles, that is a north pole and a south pole, attract each other. Similarly children, like charges, that is a positive charge and a positive charge, or a negative charge and a negative charge, repel each other. But unlike charges, that is a positive and a negative charge, will attract each other. Another question which arises here is that these charges are present in which type of particles? These charges are present in very small size particles that have very little mass called protons and electrons. Every matter around us has millions of protons and electrons in it. In some materials, like in metals, the electrons are free to move, but in non-metals, these electrons cannot move freely. At our homes, in any electrical appliance, say for example in a tube light, these electrons flow through the wire in a defined direction. So, the flow of electrons in an electric wire in a defined direction is called electric current. However, electrons were not known at the time when the phenomena of electricity was first discovered. So, the electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is given by the expression I is equal to Q upon T. Children, the SI unit of electric charge is Coulomb. An electron possesses a negative charge of 1.6 into 10 to the power minus 19 coulombs. The electric current is expressed by a unit called ampere, named after the French scientist André-Marie Ampere. 1 ampere is constituted by the flow of 1 coulomb of charge per second, that is 1 ampere is equal to 1 coulomb upon 1 second. To measure electric current in a circuit, an instrument called ammeter is used. It is always connected in series in a circuit through which the current is to be measured. Look at this diagram of a typical electric circuit. It has a cell, an electric bulb, an ammeter and a plug key, all connected in series. And notice that the electric current flows in the circuit from positive terminal of the cell to the negative terminal of the cell through the bulb and the ammeter. Electric potential and potential difference. What makes the electric charge to flow? Let us consider this by the analogy of flow of water. Take 2 beakers filled with equivalent amount of water. Connect them with the help of a tube as shown in the picture. If we examine these beakers for some time, we will observe that there is no flow of water between the 2 beakers, as there is equal amount of water present in both. But children, just try to think, how can we allow the flow of water between these 2 beakers? If we increase the level of beaker 2, then water will start flowing from beaker 2 to beaker 1. This is because raising the second beaker to a higher level will create a pressure difference between the 2 beakers. In the same way, some factor will be required for the flow of charges in a conducting metallic wire. What can be this factor? Let us try to find out. But let me make this clear to you children that gravity has no role to play for the flow of charges in a conducting wire. The electrons move only if there is a difference of electric pressure along the conductor. This is called potential difference. This potential difference may be produced by a battery consisting of one or more electric cells. The chemical action within a cell generates the potential difference across the terminals of the cell, even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expend chemical energy stored in it. So children, we can define electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to the other. Potential difference V between 2 points is equal to work done over charge, that is V is equal to W upon Q. The SI unit of potential difference is volt, named after Alessandro Volta, an Italian physicist. 1 volt is the potential difference between 2 points in a current carrying conductor. When 1 joule of work is done to move a charge of 1 coulomb from one point to the other, the potential difference is measured by means of an instrument called the voltmeter, which is always connected in parallel across the points between which the potential difference is to be measured. Children, let us now try to understand Ohm's law. Ohm's law helps to establish a relationship between the potential difference across a conductor and the current through it. According to this law, electric current flowing through a metallic wire is directly proportional to the potential difference V across its ends and inversely proportional to its resistance. Or, in other words, we can say that the more the potential difference, the more the current will flow, while the more the resistance offered by a conductor, the less the current will flow through it. Children, let us understand all this with the help of an activity. For this, we need a nichrome wire, an ammeter, a voltmeter and 3 cells of 1.5 volt each. Now set up a circuit as shown in the picture. Note the reading I in the ammeter for the current and reading V of the voltmeter for the potential difference across the nichrome wire in the circuit. Suppose with one cell in the circuit, the electric current is I1 and potential difference is V1. Note it down in the table given. Now, join 2 cells in the circuit and again note the readings of the electric current and potential difference. Tabulate them in the given table as I2 and V2. Now, in the same way, join 3 cells in the circuit and note the readings again. Tabulate them as I3 and V3. You will notice that as the number of cells goes on increasing in the circuit, the readings of electric current I and potential difference V also goes on increasing. Now, calculate the ratio of V to I for each pair of potential difference V and current I. And you will find that the value obtained for V upon I is approximately same in each case. If we plot a graph between V and I, you will see that it will be a straight line that passes through the origin of the graph. This means V upon I is a constant ratio. Children, in 1827, a German physicist, Georg Simon Ohm, found the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. He stated that the electric current flowing through a metallic wire is directly proportional to the potential difference V across its ends, provided its temperature remains the same. This is called Ohm's law. In other words, V is directly proportional to I. V upon I is equal to constant, which is R, or V is equal to IR. In this equation, R is a constant for the given metallic wire at a given temperature and is called its resistance. The SI unit of resistance is ohm, which is represented by the Greek letter ohm. According to Ohm's law, R is equal to V upon I. If the potential difference across the two ends of a conductor is 1 volt and the current through it is 1 ampere, then the resistance R of the conductor is 1 ohm. Children, let us now discuss the factors on which resistance of a conductor depends. On applying Ohm's law, we observe that the resistance of a conductor depends on its length, on its area of cross section, and on the nature of its material. Precise measurements have shown that resistance of a uniform metallic conductor is directly proportional to its length L and inversely proportional to the area of cross section A. That is, R is directly proportional to L and R is inversely proportional to A. On combining these two equations, we get R is proportional to L over A, or R is equal to rho L over A, where rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of electrical resistivity is ohm meter. It is a characteristic property of the material. The metals and alloys have very low resistivity. They are good conductors of electricity. Insulators like rubber and glass have high resistivity. Both the resistance and resistivity of a material vary with temperature. Children, here I would like to stress on one point, that the resistivity of alloys is generally higher than that of its constituent metals. Alloys do not oxidize or burn readily at high temperature. It is for this reason that they are commonly used in electrical heating devices like electric iron, toasters, etc. For making the filaments of electric bulbs, tungsten is used almost exclusively, whereas copper and aluminium are generally used for electrical transmission lines. Resistance of a system of resistors. There are two methods of joining the resistors together in combination. One is in series and the other is in parallel combination. Look at the figure 1, which shows an electric circuit in which 3 resistors having resistances R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in series. The second figure shows a combination of resistors in which 3 resistors R1, R2 and R3 are connected together between points X and Y. Here the resistors are said to be connected in parallel arrangement. Let us try to understand each case with the help of an activity using electric circuits. For this, connect an electric bulb in an electric circuit. This bulb will behave as a resistor. Plug the key to complete the circuit. You will see that the bulb glows very brightly. Now connect another bulb in series in the circuit. What do you observe on plugging the key? Yes, you will observe that both the bulbs will glow, but the brightness in the glow is lesser than what it was in case 1. In the same way, if we connect another bulb in the circuit in series, we will observe that the glow in all the 3 bulbs will further decrease, or in other words, they will glow with less brightness as compared to case 2 and case 1. So we conclude from this activity that if we go on increasing the number of resistors in an electric circuit, then the electric current will go on decreasing, or in other words, the brightness will go on decreasing. The equivalent resistance in series will increase while the electric current will decrease. Now we will make another electrical circuit. In the beginning of the activity, we will connect one bulb in this circuit, just in the same way we did in the previous activity. Before we connect other bulbs, we will connect one test bulb in series with the first bulb. This test bulb will help us to detect a change in the glow on connecting other bulbs in the circuit. On plugging the key, we will observe that the bulbs start glowing. Now we will connect another bulb in parallel to the first bulb and will notice that the flow of electric current through the test bulb has increased, due to which it will now start glowing more brightly. In this way, we will notice that if we go on increasing the number of bulbs or resistors connected in parallel to each other, then the brightness of the test bulb will also go on increasing continuously. Thus, we conclude that equivalent resistance in parallel will decrease while the electric current will increase. Heating effect of electric current and its applications. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor connected to the battery. To maintain the current, the source has to keep expending its energy. Children, have you ever wondered where does this energy go? A part of the source energy may be consumed into some useful work, and rest of the source energy may be expended in heat to raise the temperature of the gadget. We often observe this in our daily life. For example, an electric fan becomes warm if used continuously for longer time. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heaters, electric iron, etc. Consider a resistor R through which current I is flowing. Let the potential difference across it be V. Let T be the time taken during which a charge Q flows across. Then the work done in moving the charge Q through a potential difference V is equal to VQ. That means the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the source is P is equals to V into Q upon T, which is equal to V into I. Or the energy supplied to the circuit by the source in time T is P into T, that is equal to V into I into T. Now the question is, what happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in the time T is H is equal to V into I into T. On applying Ohm's law to this equation, we get H is equal to I square into R into T. This is known as Joule's law of heating, and this law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance, directly proportional to the resistance for a given current, and directly proportional to the time for which the current flows through the resistor. In practical situations, when an electrical appliance is connected to a known voltage source, then the equation H is equal to I square RT is used after calculating the current through it using the relation I is equal to V upon R. Children, let us now discuss about electric power. The rate of doing work is called power. This is also the rate of consumption of energy. Power is denoted by the symbol P. SI unit of electric power is watt. It is the smaller unit of power. Children, do you know that in actual practice, we use a much larger unit of power that is called kilowatt, and 1 kilowatt is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt-hour. The commercial unit of electrical energy is kilowatt-hour, commonly known as 1 unit. Do you know, children, that 1 kilowatt-hour is equal to 1000 watts into 3600 seconds, that is 3.6 into 10 to the power 6 watt second, which is equal to 3.6 into 10 to the power 6 joule. Children, let us now give a quick revision to whatever we have learnt in this chapter. Today we have learned that a continuous and closed path of electric current is called electric circuit. A stream of electrons moving through a conductor constitutes an electric current. Conventionally, the direction of current is taken opposite to the direction of flow of electrons. The SI unit of electric current is ampere. Ohm's law. The potential difference across the ends of a resistor is directly proportional to the current through it, provided its temperature remains constant. The equivalent resistance of several resistors in series is equal to the sum of their individual resistances. The electrical energy dissipated in a resistor is given by W is equal to V into I into T. Children, now I will ask you some questions and hope you will be able to answer them all correctly. So my first question, what is the SI unit of electric power? Your options are watt, ampere, ohm, volt. Select the correct answer from the given options. Yes, the correct answer is watt. Next, how is a voltmeter connected in the circuit to measure the potential difference between 2 points? The options are in series or in parallel. Yes, the correct answer is that a voltmeter is always connected in parallel. The next question, which instrument is used to measure the potential difference? And the options are, is it ammeter or is it voltmeter? And the answer is voltmeter. And my last question is, what are the factors on which the resistance of a conductor depends? The options are length of the conductor, area of cross section of the conductor, both A and B, and the last option, none of the above. And children, the correct answer is option C, that is both length of the conductor and area of cross section. With this, we come to the end of our today's lesson, that is electricity. Hope children, you all enjoyed learning the lesson with me. We will soon meet again with the next lesson. Till then, stay safe, stay healthy. Thank you.